Okay, today we're going to talk about the graph theory chapter. So let's look at a lawn inspector. As a part of her job, the development's lawn inspector has to walk down every street in the development, making sure homeowners' landscaping conforms to the community requirements. Naturally, she wants to minimize the amount of walking she has to do. It is possible for her to walk down every street in the development without having to do any backtracking. Well, you might be able to answer that question just by looking at the picture for a while. It would be ideal to be able to answer the question for any picture regardless of the complexity. To do that, we need to simplify the picture into a form that is easy to work with. We can do that by drawing a simple line for each street. Where streets intersect, we will place a dot. This simplified picture is a graph. So here's the neighborhood, here's the graph. And let's run through some definitions real quick. A graph consists of a set of dots called vertices and a set of edges connecting pairs of vertices. A vertex is a dot in the graph that could represent an intersection of streets, a landmass, or a general location like work or school. Vertices are often connected by edges. Note that vertices only occur where a dot is explicitly placed, not whenever two edges cross. So these intersections here, well, there's none in this graph. There may be intersections that are not vertices. If there's not a dot there, it's not a vertex. Imagine a freeway overpass. The freeway and side streets cross, but it's not possible to change from one side of the street to the freeway at that point, so there is no intersection and no vertex will be placed. Edges connect pairs of vertices. An edge can represent a physical connection between locations like a street, or simply that a route connecting the two locations exists, like an airline flight. A loop is a special type of edge that connects a vertex to itself. We don't use loops much in street network graphs. The degree of a vertex, now this is important. It gets confused with degrees of an angle quite frequently. The degree of a vertex is the number of edges meeting at that vertex. It is possible for a vertex to have a degree of 0 or larger. A path is a sequence of vertices using the edges. Usually we are interested in a path between two vertices. A circuit is a path that begins and ends at the same vertex. A connected graph, or a graph, is connected if there is a path from any vertex to any other vertex. And then we have something called weights. Depending upon the problem being solved, sometimes weights are assigned to the edges. The weights could represent the distance between two locations, the travel time, or the travel cost. It is important to note that the distance between two vertices in a graph does not necessarily correspond to the weight of an edge. So the length of the edge doesn't necessarily mean that it's shorter or longer based on the length of the edge. You have to look at the weights. So we have an example here. Graph below shows 5 cities. The weights on the edges represent the airfare for a one-way flight between the cities. So we go to red. How many vertices and edges do we have? Well, let's start here in Seattle. 1, 2, 3, 4, 5 vertices. Okay. How many edges? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 edges. Is this graph connected? Well, looking at it, we can see that every vertex has an edge that goes to every other vertex. So in other words, you can get there from here. So yes, it is connected. What is the degree of the vertex representing LA? Again, degree refers to how many edges go into that vertex. 1, 2, 3, and 4. If you fly from Seattle to Dallas to Atlanta. Is this a path or a circuit? Remember, a circuit, you end up in the same place you started, so this must be a path. Let's look at it here. I'm going to go from Seattle to Dallas to Atlanta. That is a path. Okay, what about LA, Chicago, Dallas? Oops, I did that backwards, didn't I? LA to Chicago to Dallas to LA. Well, that is a circuit. We ended up where we started. Okay, now we get to the theory part of this. We have something called Dijkstra's algorithm. So we mark the ending vertex with a distance 0 and designate the vertex as current. Find all vertices leading to the current vertex and calculate the distances to the end. Since we already know the distance, did we skip something? Nope. Since we already know the distance the current vertex is from the end, this will just require adding the most recent edge. Don't record this difference if it's longer than a previously recorded distance. Mark the current vertex as visited. Never look at it again. Mark the vertex with smallest distance as current and repeat. So suppose you need to travel from Tacoma here to Yakima here. Looking at a map, it looks like driving through Auburn here and Mount Rainier here might be the shortest route. But it's not totally clear since that road is probably slower than taking the major highway through North Bend. A graph with travel times in minutes. So this is travel times in minutes. Is shown below. An alternative path through Eatonville and Packwood is also shown. Calculate the shortest path using Dijkstra's method. So we're ending at Yakima. That's here. So what's it say? Mark the ending vertex with distance 0. So that's 0. Okay, this is the current vertex. We're good there. Find all vertices leading to the current vertex. So that would be this one here, and this one here. Since we already know the distance to the current distance from the end, this will just require adding it to the most recent edge. So 0, so this becomes 104, this becomes 96, and this becomes 76. We want the shortest path here, which is this here. Okay, so that's current. And now we forget about Yakima and go to P. Okay, so now let's get rid of this for now. Okay, now I'm here at P. I have two possibilities. I can go here to E, which would put me at 192. Or I could go here to M, which would put me at 103. So M would be the shortest, MR, excuse me. However, if you remember from before, we could get to MR straight away. So bring that back to 96. So now we're here at MR, going this way. Okay, and we can get rid of all this. Now we want to get from MR, where can we go? We can go to P here, which gives us our 123 again. And we can go to this A here, which gives us our 175. So what's going to happen here is, well, it's shortest to go to P, but then what happens? Well, we go here to E again. And again, we're looking at, well, if we go this route, we're looking at what, 219. However, if we went the other route, it was 172. So now we're back to that previous path. So now we're looking at this again, and we're at 172. Let's keep this up here because I think we may want to consider it. So now we're here at E, and we want to get to T. So that's what, 120, 229? However, if we go this route, it's 190, 195. So it turns out our shortest route is this one at 195. And that's how it's used. That can get a little confusing. I think there may be homework problems. I know there's not an exam problem like that. So here we're going from A to G, and we want to go here to here. So you mark Z, D is 0. So we can go to E, which is 7, or we can go to F, which is 6. Well, typically we go to F, which is 6. And now we're here on F. We can go to D, which is 10, or we can go to C, which is 11. So we go to D, and we're at 10. Now we can go from D to B, which is 13, or to C, which is 13. Okay? But going the other way, this was 11. So let's stick with the 11. So now we've gone G, F, C, and we go up here, and this is 15. However, if I go from B to A, it's only 14. So my path is this. A, B, D, G. And the path up here was T, A, M, R, Y. So that's how that method works. Get a little confusing. I'll be openly honest with you on that. An Euler path is a path that uses every edge in a graph with no repeats. Being a path, it does not have to return to the starting vertex. So find an Euler path in the graph below. Well, again, I want to use every edge, so I can go from A to B. Is that going to work? I don't see that working. So let's try something else. Let's try starting at... No, I know what happened. As we'll learn shortly, we need to start at one of these points. Okay, I'm going over a path that does not return to the start, does not have to return to the starting vertex. That's where I messed up. You can, but you don't have to. So I can simply go A to B, or B to D to C to B to A to C. And that would be an Euler path. There's several of them, but that would be one. Now, an Euler circuit is a circuit that uses every edge in a graph with no repeats. Being a circuit, it must start and end at the same vertex. So let's start up here at D. I need to go through every vertex, or every edge. So we'll start with D. We'll go to A. Then let's go over here to E. Then let's go down here to C. Then let's go down up here to A. Go down to B. Go over to C. Go to F. Go to E. And back up to D. And then we have our Euler circuit. Every edge. Okay, next we have Euler path and circuit theorems. A graph will contain an Euler path if it consists of at most two vertices of odd degree. A graph will contain an Euler circuit if all vertices have even degree. So let's look at this. Consider the graph below. Does the graph have an Euler path or an Euler circuit? Well, we have A, B, C, D, and E. And let's find the degree of each of them. A is 1, 2, 3, 4. B is 1, 2. C is 1, 2, 3, 4. D is 1, 2, 3. And E is just 1. So what we have, an Euler graph will contain an Euler path if it contains at most two odd degree vertices. So we have an Euler path. The graph will contain an Euler circuit if all vertices have an even degree. No Euler circuit. So go back to our housing development. And is there an Euler circuit? So let's see, what do I have here? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, Q, R. So here's A, 2. Here's B, 1, 2, 3. Here's C, 1, 2. Here's D, 1, 2. Here's E, 1, 2, 3. Here's F, 1, 2, 3, 4. G is 1, 2, 3. So what do we know? We already got 3 vertices with odd degrees, so that tells us no Euler path, no Euler circuit. So she wouldn't be able to do it without counterbalancing. Okay, Fleury's algorithm. Start at any vertex. If finding an Euler circuit. If finding an Euler path, start at one of the 2 vertices with odd degree. Use any edge leaving your current vertex, providing deleting that edge will not separate the graph into 2 disconnected sets. Add the edge to your circuit, delete it from the graph. Continue until you are done. So let's do this. Let's go back to red. Let's enlarge this a little bit. And I'm going to delete it by putting it in red. So looking at our degrees here, A has degree 2, B has degree 2, C has degree 2, D has degree 4, and E has degree 2. So, start at any vertex when finding a circuit. Are we finding a circuit? Yes, circuit. So, I'm going to start here at D. And let's just go ahead and go over here to A. Okay, taking away that edge didn't hurt my graph any. So here we're going to go the only way we can go, which is here. And then, of course, here we're going to go the only way we can go. We have D, A, C, D, And let's go B. We could have went E. Now we go E, and then we go D. And that is our Euler circuit using Fleury's algorithm. Okay, does the graph below have an Euler circuit? So find one. I have A, B, C, D, E, F, and G. A has degree 2, B has degree 4, C has degree 4, D has degree 4, E has degree 4, F has degree 4, and G has degree 2. So it does have a circuit. So let's do this. Let's start here at A, and we'll go to C. Then we could go to D, down here to F, up here to G, up here to E, down here to F, over here to C, up here to B, down here to D, up here to E, over here to B, and lastly back to A. And there we go. Okay, I don't do this Eulerization. You can read up on it if you want, but I don't use it. Next, they call it Hamiltonian. I learned it as Hamilton. So if I mess up and call it Hamilton, I mean Hamiltonian. Hamiltonian circuits and paths. A Hamiltonian circuit is a circuit that visits every vertex once with no repeats. Being a circuit, it must start and end at the same vertex. A Hamiltonian path also visits every vertex once with no repeats, but does not have to start and end at the same vertex. Find a Hamiltonian circuit on the graph below. Notice that the circuit only has to visit every vertex once. It does not need to visit every edge. So something simple like this. Boom, boom, boom. Let's draw some arrows for direction. That work? That's not going to work, is it? How about we do this? Come down here, go up here, and like this, and like that, and like that, up like that, and up like that, and we have our circuit. Every vertex, not every edge. That's the difference. Euler is every edge, Hamilton is every vertex. Does a Hamiltonian path or circuit exist on the graph below? Well, I can tell you straight up, a circuit doesn't exist. Because in order for a circuit to exist, we have to be able to go in and out of each vertex, and E here does not have one. So no circuit. And we'll come up with an algorithm to show that here shortly. Let's see if we can hit every vertex, though. I think we can. So that'll work. We have E, C, D, A, B, and that is a Hamiltonian path. No circuit, but we do have a path. We can hit every vertex without repeating. Okay, so now we have what's called a brute force algorithm. The first step in this is to list all possible Hamiltonian circuits, find the length of each circuit by adding the edge weights, and select the circuit with the minimal total weight. So what I'm going to do is I'm going to pause this while I go through all the circuits, and then I'll bring it back up. Okay, so I've listed here all 24 possible Hamiltonian circuits. Now, The thing is, I've marked them. This one and this one are the same, just backwards. This should be CB or BC. Yeah. So we can immediately count out half of our things. 1, 2, 3. 1, 2, 3. Now we have 12. And keep in mind, this is only 4 vertices. So brute force would be go through here and calculate all of these. I'm not going to calculate all of them. Let's just look at the A's here. I can go from A to C, which is 2. To D, C to D, which is 8. To C again, or B, I'm sorry. D to B, which is 9. A, C, D, B, A, which is 4. And this is 23. That's this one here. Let's do this. A, D, B, C, A. So A to D is 1. D to B is 9. B to C is 13. And C to A is 2. And this is 10, 22, 25. And that's this one here. Let's do this one more in the A. A, D, D, B, A. So we start with A to D, which is 1, plus D to C, which is 8, plus C to B, which is 13, plus B to A, which is 4, and this gives us 26. So right now, this one here appears to be the shortest. And the thing is, we'd have to do that through every one of these. So there's 12 of them. That's 3 of them. And find the shortest one, and that's how this works. So here's some help for you to figure this out. So the number of possible circuits or n circuits in a complete graph. A complete graph means that every circuit or every vertex links to every other vertex, like this one here. Go from any vertex to every other vertex, so it's complete. For n vertices in the complete graph, there will be n minus 1 factorial, which is n minus 1 times n minus 2, all the way down to 3 times 2 times 1 roots. Half of these are duplicates in reverse order, which is what we noticed. So there are n minus 1 factorial unique circuits. In case you didn't know, the explanation symbol is read as factorial and is short for the product shown. A complete graph is a graph where every vertex is connected to every other vertex. So if we have a graph with 3 vertices, how many circuits would a complete graph with 3 vertices have? Well, n minus 1 factorial, which is n is 3 minus 1 factorial, which is 2 factorial, which is simply 2 times 1, or 2. Okay, what about how many circuits would a complete graph with 8 vertices have? That would be 8 minus 1 factorial, which is 7 factorial. Wait a minute, we forgot to divide by 2, which is 1. Okay, so now I have 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2. Okay, let me get my calculator. And I get 5,040 over 2. Divide that by 2, and I get 2,520. How would you like to brute force all of those? They could do it with a computer, but it would still take a while. So we've come up with something called the nearest neighbor algorithm. So in the nearest neighbor, it's a 3-step process, basically. Except one of the steps is repeated. So we start and we find a starting point. Doesn't matter where. Pick one. Move to the nearest unvisited vertex, i.e. the edge with the smallest weight, and repeat until the circuit is complete. So consider this graph here. Let's start with A, since it's right here at the top. I'm starting at A. I need to end at A. Where's my closest vertex? Well, that's D at 1. And go ahead and make a note down here. Now, I can go to B or I can go to C. Well, it appears that C is closer at 8. So C, and we're going to add 8. Now, I can't go to A, so I have to go to B. And that has a weight of 13. And then I'd go back to A, which has a weight of 4. And this has a weight of 26. And I didn't even read this part where it says start at A, so we started at A. Okay, in this case, we ended up finding the worst circuit in the graph. Unfortunately, the nearest neighbor algorithm is a greedy algorithm, meaning it only looks at the immediate decision without considering the consequences in the future. So, here we go again. Go back to this original graph. Consider the salesman starting in Seattle, so we're starting in Seattle. Use the nearest neighbor algorithm and find the total cost of the resulting circuit. Is this the optimal, cheapest circuit? Okay, so we're going to start at Seattle. Where's our nearest neighbor? Well, this is 70. That looks like it. 145, 120, and 140. So then I'm going to LA. And there I am, I'm in LA. And here's 100, here's 150, and here's 170. So it looks like I'm going to Chicago. That's 70, and this is 100. Okay, now I'm in Chicago. Going to Dallas is 165, so I guess I'm going to Atlanta. Atlanta, which is 75. Then I don't have a choice. I'm going to Dallas, which is 85, and then I'm going back to Seattle, which is 120. $70 plus 100 plus 75 plus 85 plus 120 is $450. Now looking at that, that's probably the shortest method, because if you look, the largest distance here, or the largest dollar value here, is 120. And I don't have any other routes that are less than that. So this is probably the cheapest circuit in this case. Now this brings us to the repeated nearest neighbor algorithm, in which case we do the nearest neighbor algorithm starting at each vertex. And then we choose the shortest one. So we're going to do the nearest neighbor algorithm starting at A. So start at A. My nearest neighbor is D, which is 1. Then my nearest neighbor is C, which is 8. Then the only neighbor left is B, which is 9. And then back to A, which is 4. And that was what? Did I miss one? Yes, I missed one. C to B is 13, and then 4. Okay, starting with A, this is what, that 2060? No, this is, hold on a minute. We have A to D, which is 1, D to C is 8, C to B is 13, and B to A is 4. Somehow I got an extra number in there. And this was 26. So now let's do it starting with B. My nearest neighbor is A, which is 4. Then my nearest neighbor is D, which is 1. Then my nearest neighbor is C, which is 8. And then I go back to B, which is 13. 21, 22, that's 26 as well. Okay, now let's start at C and see what we get. Okay. That's intriguing. So let's start at C and see what we get. Okay, my nearest neighbor to C is A with 2. My nearest neighbor to A is still D with 1. That only leaves B left to C, or yeah, B left to go to, which is 9. And then back to C, which is 13, 22, 23, 25. And then let's look at D. Closest to D is A, which is 1. Closest to A is C, which is 2. That only leaves B left, which is 13. And then we go back to D, which is 9, 22, and 25. So we actually have 2 that are the same. And that can happen. Okay. Okay. So now instead of having a graph, we have a table here. Table below shows the time in milliseconds it takes to send a packet of data between computers on a network. If data needed to be sent sequenced to each computer, then notification needed to come back to the original computer, we would be solving a TSP. Computers are labeled A to F for convenience. So find the circuit generated by the NNA starting at B, nearest neighbor method. So we're here at B. We're starting at, this is A. Starting at B, what's closest to B? It looks like E is closest to B with 24. So now I'm on E. What's closest to B to E? It looks like D at 11. So now I'm here at D. What's closest to E? Well, E is with 11, but I can't use that. So it looks like A with 12. So now I'm at A. What's closest to 12? Again, it's D, but I've already been there. Let's C and F are all that's left. Can't go to D. Then comes C, which works out. So now I'm at C with 34. I'm at C. The only place left to go is F. C to F is 27. And then back to B. And F to B is 50. So what's that? 24 plus 11 plus 12 plus 34 plus 27 plus 50. And that is 158. Now, the repeated nearest neighbor method, well, we have to do the other letters. I'm not going to do them all. I'm going to let you do that. So let's just start with A. Nearest neighbor to A is D, and that's 12. So now I'm at D. The nearest neighbor to D is E, which is 11. The nearest neighbor to E that I haven't used already is B at 24. Nearest neighbor to B that I haven't used already is C at 31. The nearest neighbor to C, A, B, C, D, E. I haven't used F. That's the only one left. F to C is 27. And then back to A, which is 41. Let's add these up, See what we get. And I get 145. So that's a little bit better. So now we have A and B. We would do C, D, E, and F as well. And see what we get. Same process. Okay. Next, we have something called the sorted edges algorithm. Select the cheapest unused edge in the graph. Repeat step 1, adding the cheapest unused edge to the circuit, unless adding the edge would create a circuit that doesn't contain all vertices, or adding the edge would give the vertex degree 3. Repeat until a circuit containing all vertices is formed. So we're going to find the cheapest edge. So that's this one here, 1. We got A to D. Next cheapest edge is A to C. And that's 2. Now, our next cheapest edge is A to B, but that would give A a degree of 3, so we can't use that. Next cheapest edge would be C to D, but that would give me a circuit, so we can't use that. So my next cheapest edge is DB, which is 9, and then the other edge is BC, which is 13. And this is 25. So this would be our circuit using this method. I think that was the shortest edge, the shortest circuit, so that worked out pretty well. Okay, here we go. Find a circuit produced by the sorted edges algorithm using the graph below. So let's see, what was our shortest edge? It's 11 here. Okay, I see a 13. Are there any 12s? No. So this one here, B to G, which is 13. I have a 14 here. A to E, which is 14. Now I can't go back to A or B at all again. Okay, looks like I have a 15 here, E to F. So I can't go to A. Okay, that was 15. Here's a 17, but that goes to E, so I can't use it. Okay, here's a 19. I can do that. No, I can't do that. That gives me a circuit. Don't know what's going on with my computer here. So I guess we'll just go to this. Okay. Looks like 23 here, but that's B. I can't use it. 25, that goes to B. I can't use it. Here's a 27, but that goes to A. I can't use it. So it looks like a 33, that goes to A. Can't use it. I have a 36. I can use it. That's what, G to C at 36. And then where are my... A has 2, B has 2, E has 2, C has 2, F. C to F, which is 37. This one can get a little confusing, especially when you have so many vertices. And note, the letter D is missing, and it was probably going to go there, and they decided not to. So they just left it off. So what's my circuit? The circuit here is 111. That's the weight of it. So again, that's just another method to find this. So now we're going to talk about spanning tree. Spanning tree is a connected graph using all vertices in which there are no circuits. In other words, there is a path from any vertex to any other vertex, but no circuits. The minimum cost spanning tree is a spanning tree with the smallest total edge weight. So we have Kruskal's algorithm, and it works kind of like the sorted edges algorithm. Select the cheapest unused edge in the graph. Repeat step 1, adding the cheapest unused edge, unless adding the edge would create a circuit, and repeat till you have a tree. So basically, we want to keep choosing edges till every vertex is reached, no circuits. So my cheapest edge appears to be this one here, AB. It doesn't say we can't visit it more often. So AE. Now I can't go to 6 here, because that could give me a circuit. So there is the 7 here, DC. Then I have an 8 here. Actually, yeah, I have to connect CA. So now I can get from D to A, D to C, D to B, D to E, A to E, B, C, and D, B to A, E, C, and D, and so forth. So that is it. That is my spanning tree. And it should be a minimum cost of 24. Okay. Again, find the minimum cost spanning tree. Same graph. I have AB here, which is 11. Didn't have a 12, but I have this BG at 13. Now let's do this. A, B, D, E, F, and G. Because once we get all the letters gone, we can pretty much be done. Okay, so I got this 14, which is A, E. Okay, I got this 15, which is AG, gives me a circuit, so I can't use it. I got the 16, which is EF, gets rid of F for me. That's an E. That's 16. And then the only place left I have to go is C. So what's my shortest to C? That would be BC at 25. And there we go. We can get to every vertex from every other vertex. There are no circuits. So let's see what our weight of our spanning tree is. And this weight is 79. Probably thinking, what are real world applications of this stuff? Besides the traveling salesman, which probably don't exist anymore for the most part. Well, think of this as a group of buildings, a college campus. And you want to wire it, you want to wire new cables, electric cables, phone cables, whatever. You don't need to make it where the wires go to every building from every other building. You just need to make it where the wire goes from each building to every other building. And that's where the spanning tree would come in. And you'd want to do it with the minimum amount of wire, and that's where the minimum spanning tree comes in. So that's it for this chapter. You guys have a good day, and I will see you next time.